And we will equivalence of the Kelvin, Planck and Clausius statements of the second law of thermodynamics. So we have already seen the two statements separately, and we have seen that Kelvin-Planck statement discusses the limitation of working of a heat engine, which says that any heat engine can never be having 10% efficiency, or the efficiency of a heat engine can never be equal to unity, or there should always be some heat that is rejected to the sink. QL can never be equal to 0. That was the essence of the Kelvin-Planck statement. So the Kelvin-Planck statement was related to heat engine, limitation of heat engine, and it was summarized as eta not equal to 1 or QL not equal to 0. That is, there should be at least some heat energy that is rejected to the low temperature reservoir. You cannot have a heat engine working with a single reservoir. That was the essence of the Kelvin-Planck statement. Now in the Clausius statement, it was talking about the limitation in the performance of a refrigerator. So the Clausius statement is related to the limitation in the working of a refrigerator, and which says that the coefficient of performance of a refrigerator is never equal to infinity, or it is said that there should be some external work, W not equal to 0, for transferring heat from a low temperature reservoir to a high temperature reservoir. It cannot flow by itself from a low temperature reservoir to a high temperature reservoir. So these were the two statements. Now our aim is to prove that the two statements, even though they are stated in terms of two different devices, they are actually equivalent, or they mean the same essentially. So our purpose is to prove that these two statements are equivalent. Means either you can depend upon the Kelvin-Planck statement, or you can depend upon the Clausius statement in order to check whether a given situation is obeying the second law of thermodynamics or not. It's actually a matter of situation, right? So in order to prove that, we are going to use a certain type of a method, and for the particular method we will be using a particular set of notations. It's just a logical method of proving something is correct or something is wrong. So let's adopt certain conventions first. So this is the convention first. So you have got two statements, suppose that. So suppose that you have got two statements or two propositions. Okay, so you have two statements. What are the statements here? The statements here are Kelvin-Planck statement and a Clausius statement. Okay, so for that you have got two statements. Now these two statements are said to be equivalent. Two statements are said to be equivalent. Said to be equivalent. That's what we are going to prove. Said to be equivalent if the truth of one implies the truth of the other. Implies the truth of the other. So if one is correct, then the other one is also correct. If that is a condition, we can say that the two statements are equivalent. Truth of the other. This is a strategy that we are following. Truth of the other. That is one way of proving that two statements are equivalent. Okay, the two statements are said to be equivalent if the truth of one implies the truth of other. Okay, so if one is proved to be correct, then automatically the other will be proved correct. That's the meaning. Or you can go for another method. Another strategy can be adopted. What is that strategy? It's known as the falsity strategy, or falsity means wrong. Falsity of one statement implies the falsity of the other. Implies the falsity of the other. Falsity of the other. So this is the strategies. Any of these strategy can be used to prove two statements are equivalent. So let's use the falsity strategy. Means I am going to use the second strategy. So this particular strategy we are going to use to prove that the Kelvin, Planck as well as Clausius statements are really equivalent. So in order to prove this one, we are going to use certain notations. So these notations are used so that we can minimize writing in sentences or words. Okay, so let's adopt certain notations. So let me introduce the notations here. So here K denotes Kelvin Planck. Always remember K stands for the Kelvin Planck statement, K, and C stands for Clausius, right? So these are the notations we are going to use. K denotes, if we are writing K plus K actually, plus K or simply K. K denotes truth of the Kelvin Planck statement. When I write K, it means that Kelvin Planck statement is true. And if I write minus K, it denotes the falsity. So this minus denotes falsity, and we are not putting plus, it is plus K, right? Okay, so simply writing K denotes the truth, right? So in the same manner we can see simply writing C denotes truth of Clausius statement, and minus C denotes, this minus denotes falsity, minus C denotes the falsity of the Clausius statement. So these are the notations that we are going to use. That's a standard notation that is adopted in such strategies, right? Now two more symbols let me use. See, I'm going to use this particular symbol. This is a symbol. This symbol means implies. Implies. What is meaning imply? Leads to, concludes. That's meaning implies. And I'm using this symbol. This symbol that means equivalent. So I have now by the time introduced 6 notations that we'll be using in the argument. So once it is familiar, it's quite simple. It's a very simple task that we are going to do, right? So these are the notations that we are going to use. So now let's see how to prove the equivalence. So as I told you, we'll be using the falsity statement, and we can do the proof in 2 different ways. Okay, so let's see how we are going to do that. So this is what we are going to do first. So just see that this is our first method. One of this is enough. So we are minus C implies minus K. Implies minus K. So let's try to interpret it until you become familiar with the notations. What is minus C meaning? C denotes Clausius statement. So what is minus C? Minus C denotes falsity of Clausius statement. Okay, is it not very brief now? Minus C denotes that falsity of Clausius statement. Means if Clausius statement is false, or if Clausius statement fails. Okay, what is the symbol imply? Implies. Implies falsity of Kelvin statement. If one is wrong, the other is also wrong. If one is correct, the other is also correct. That's what we are going to prove. Okay, so we are going to prove that if the Clausius statement is not obeyed, then automatically the Kelvin-Planck statement is also violated. This is what we are going to prove. So let's see how to do that one. So to do this, you can just see on the screen. So I have drawn an engine. Okay, I have drawn an engine. See, there is a speciality you can note. So you can see part of the refrigerator and an engine. A heat engine and a refrigerator are imagined to be walking between the same two heat reservoirs. So you have high temperature reservoir here, you have a low temperature reservoir here, and a heat engine and a refrigerator are supposed to be sharing the two reservoirs. The same two reservoirs are being shared by both the heat engine as well as the refrigerator. Okay. Now see that you just look at the right side. The right side shows a heat engine. So as per the schematic diagram what you have learned already, you can see a heat engine is drawing or absorbing an amount of heat QH from a high temperature reservoir. It rejects an amount of heat QL to the low temperature reservoir, and some amount of work W, which is equal to the difference between QH and QL, is converted into useful work. So you can see the engine is working perfectly. So the engine is not violating the Kelvin, because it's a normal engine working. So this complete diagram is there. But you look onto the left side, okay, where we are trying to show a refrigerator. Okay, a refrigerator is there. So let's see, is the refrigerator working conditions are met completely? You will see that there is something missing. What is missing? So the refrigerator is shown to be absorbing QL amount of heat from the low temperature reservoir, and it is just rejecting the same amount of QL to the high temperature reservoir. And what is missing here? There is no work input, no work input. So I can say that this is a no work refrigerator. That is why it is named here as a no work refrigerator. Means this refrigerator is violating, is not violating which statement? Is violating the Clausius statement. So the refrigerator that we have considered here is violating the Clausius statement. Okay, whereas individually this heat engine is not violating the Kelvin-Planck statement. Heat engine is perfect, but our refrigerator is violating the Clausius statement. That is what we have taken here. So we have already taken that the Clausius statement is violated. So now, if the Clausius statement is violated, we have to prove that it will be leading to a violation of the Kelvin-Planck statement as well. That is what we are going to prove. So let's see how to argue. Remember, it's a logical argument. Okay, that's the method. So this is the logical argument. You consider, since you can see that the high temperature and low temperature reservoirs here are both same, I have the freedom to consider the devices as a single device. So let me consider these two devices as single device. So let me do it like this. So I'm just drawing it like this. I'm going to consider these two devices as a single device, right? So I'm just drawing a block here so that you imagine that these two devices as a single device, and this single device can be considered, means the refrigerator and the heat engine together forms a refrigerator. I can write like this: refrigerator plus heat engine together, it forms what is known as a self-acting machine. You can consider now as a single machine. That's what is known as a self-acting machine. Okay. Now let's see what's the sole result. What's the sole effect of the this machine? So you can see that QL amount of heat is taken from the. Let's individually look at the reservoirs. QL amount of heat is absorbed from the low temperature reservoir by this machine. So this QL is absorbed, but you can see that at the same time QL is given back. So QL is taken, say 100 joule is taken and 100 joule is given back. So means there is no change in effect happening for the low temperature reservoir, right? And let's look at the high temperature reservoir. What is happening? QH amount of heat is taken by the machine and it is giving QL amount of heat to the high temperature reservoir. Means they are not balanced. Say that suppose QH is equal to some 600 joules, okay, and QL is equal to some 100 joules as I have taken here. So here it is 100 joules again, right? So this is also 100 joules. So 100 joule taken and 100 joule given. So there is no net effect here. So you can see that QH 600 joules of heat is taken and some 100 joule of heat it's getting here. So what about the high temperature reservoir? There is a difference. There is some net effect for the high temperature reservoir. What is the net effect? It has lost some 600 minus 100 means 500 joules of heat. So I can say that the net effect for the high temperature reservoir is that an amount of heat equal to QH minus what it has got. QL has been absorbed from the high temperature reservoir. And let's see what is the outcome. You can see that the combined system, this self-acting machine has done a work which is equal to how much? QH minus QL, right? I think we are able to just summarize the thing. So the refrigerator and heat engine together can be considered as a self-acting machine whose only effect or net effect is to extract QH minus QL amount of heat from the hot reservoir and convert this heat into work. All this heat is converted into work without producing any change in the low temperature reservoir. Remember, this process is not causing any change in the low temperature reservoir. Means there is no any role of this low temperature reservoir at all, right? Okay, so what does it mean? Is it not implying a violation of our Kelvin-Planck statement? So the Kelvin-Planck statement is violated by this combined machine, okay, is violated because you have seen that whatever heat is drawn from the high temperature reservoir has been entirely converted into work by this combined machine. So there is a clear violation of the Kelvin-Planck statement. I think that is enough. Okay, so what I have proved is that the falsity of Clausius statement leads to, or it implies, falsity of falsity of the Clausius statement I can use the symbol. This is the implies the falsity of the Kelvin-Planck statement. So we are able to prove it. So it's a very clear logical argument. So I think you understood what is the technique to be used. Okay, you consider that the refrigerator is violating Clausius statement, and our heat engine alone is not violating Kelvin-Planck statement, and you consider that these two devices are sharing the same set of reservoirs, and if you consider the two devices to be a single device which is acting as a self-acting machine, then you will see that the net effect will be to absorb certain amount of QH minus QL from the hot reservoir and converting that entire heat into work, which is a clear violation of the Kelvin-Planck statement. So we can prove that very easily, right? So now we will be doing the same technique or same argumentative technique to prove the reverse of the fact. So what will be the reverse of the fact? So reverse will be that we assume that the Kelvin-Planck statement is violated, means heat engine is not perfect or heat engine is violating the rule. Then we will show that it will imply the violation of the Clausius statement. Then the Clausius statement also will be violated. This is our next step. I think we will be able to complete that in the same manner, same logic. You can do it. You can write, but I am doing for the time being. Okay, so let's go to the next slide. See, here you just have a look at look at the just schematic diagram drawn over here, you can expect what will be correct and what will be wrong there. See, you can look at the right side. The right side is showing a refrigerator. Actually, it is a perfect refrigerator. It is not making any violations. You can see because the refrigerator is drawing QL amount of heat from the low temperature reservoir. Some work is obtained from outside somewhere. Some work is obtained from outside, and using that work, okay, it is just what is that? Depositing certain amount of heat, which is equal to the work. This is actually the work that it has obtained, work plus QL. So that was the real performance or the real working of a refrigerator. So the refrigerator is okay. So this is okay. No violation of Clausius statement, right? But you look at to the left side. What is the left side? Left side is showing part of an engine. I should not call it as a complete engine because it should not be given the status of a complete engine, right? Why? You can understand why. Because the engine is shown to be drawing QH amount of heat from the hot reservoir, and it is shown to be doing work. So this is work, and how much work is done? How much heat it has absorbed, QH amount of heat it has absorbed, and it is converting the entire absorbed heat into useful work. Means without rejecting any QL to the low temperature reservoir. Means this heat engine is now working using a single reservoir. Only hot reservoir is enough for this working. But you know that's a clear violation of which one? Clear violation of the Kelvin Planck statement of the second law of thermodynamics. Means so I can call this engine as a no sink engine. This is an engine without a sink, which is actually let's say violation. No sink engine. I am calling it as a no sink engine, right? So this is violating. So this engine violates. This is what you have to see. This engine violates the Kelvin Planck statement. That is our idea to begin with. So that is what is given here. Proof of violation of Kelvin Planck statement implies violation of the Clausius statement. That is what you have to do. So previous thing what we have done, we have proved the reverse. Minus C implies minus K. That is what we have done. So I think you can just look at the diagram and do the argument by yourself. See what is the thing? Just look at the diagram. You consider like what you have done in the previous case. Let me think. I'm considering the two machines together. So I'm considering the two machines together now like this. This is what I'm going to do. Okay. So two are combined because anyway they are operating between the two same set of reservoirs. So there is nothing wrong in this argument. So I'm single unit. So this is now acting like a self-acting machine. The combination acts as a self-acting machine which operates between the two reservoirs. Now what is the net outcome? Let's see what's the net outcome. See, the net outcome is that let's look at the high temperature reservoir for the time being. What is the high temperature reservoir? It has lost QH amount of heat. QH amount of heat is taken from here. QH amount of heat is taken from the high temperature reservoir, and that during the process this QH amount of heat is given back also. So QH amount of heat taken and QH amount of heat is given back. Not only QH amount of heat is given back, it is getting some additional supply of QL amount of heat. So what is the net effect on the high temperature reservoir? It has gained, I can say, it has gained QL amount of heat. Gained QL amount of heat. That is the net effect. Now let me look at the low temperature reservoir. What is the low temperature reservoir? See, it has got nothing from the heat engine, no receipts, but it has lost how much? QL amount of heat. So lost QL amount of heat. Is it correct? Okay. And is there any that is flowing out of the system? No, because whatever work is done, that work is used to operate a refrigerator. See that. That's what is shown here. That is the arrow has been shown in between. the work output of the engine is used as the work input of the refrigerator. That is why there is nothing outside, right? So suppose that some 600 joules of heat was drawn by the heat engine, and that 600 joules of heat is entirely converted into work, and that 600 joules of work is used by the refrigerator to transfer some 100 joule of, say 100 joule of heat from the low temperature reservoir to the other one, you say. That's the way in which it is done. Or you can do it in the reverse also, depending on the coefficient of performance. This example may not be suiting, it doesn't matter. Okay, see that is what, okay, maybe this value will be a bit higher because the coefficient of performance will be always greater than 1, right? So this is the thing. So what is the net effect here? The net effect is that QL amount of heat is taken. QL amount of heat is taken from the low temperature reservoir, and that QL amount of heat has been deposited onto high temperature reservoir without any external work. There is no any external work here. W is equal to 0 here, but I am able to just take QL amount of heat from here and deposit it here, transfer. So is not against the direction of spontaneous flow of heat, because from low heat cannot flow without any additional input work to a high temperature reservoir, which is a clear violation of the Clausius statement of the second law of thermodynamics. Remember one thing, that here is a work, but this work is purely internal. Okay, this work is not obtained outside. That is why I have just taken that these two systems are a block. So this work is entirely used up by the system itself internally. So there is no any external work you are getting from outside. So it's a clear violation of the what do you say, the Clausius statement. So we have proved that the falsity of Kelvin-Planck statement. If Kelvin-Planck statement is violated, then it implies that the Clausius statement also will be violated. Okay, so hope you are able to understand what is the logical way of arguing at the equivalence. So our proof is that, our conclusion is that the Kelvin-Planck statement is equivalent to, I am using the symbol here, Clausius statement. The Kelvin-Planck statement is equivalent to the Clausius statement. Okay, so that's the argument. So if you are asked to prove that two statements are equivalent, you can either go by the first method, or you can go by the second argument. And if time permits, you can always do both the arguments to show that at any cost the two statements are equivalent, right? So we conclude it this way. Remember, the second law of thermodynamics can be stated in different forms, which are all equivalent. So in the point of view of working of a heat engine, it is stated in terms of the Kelvin-Planck method, or if you are focusing on the working of a refrigerator, it can be stated in terms of the Clausius statement, right? Even though the language of statement or the focus of the statement are different, they mean the same. They give the same result as far as the second law of thermodynamics is concerned. Okay, that's all. Thank you.